So we're kind of continuing the development of first-order logic exactly like we did, exactly like we did a propositional logic. So first, syntax, what it looks like, then semantics, what it means, and finally, proof theory, how you prove stuff. So a kind of fairly syntactic lecture coming up. Today we get to see that 1 + 1 is 2, by the way. That'll be later on as a little surprise. First, some boring stuff. So to remind you, of course, shall I switch off the lights? Turn it down a bit. Is that better? And there's a question. It's on. Yeah. Okay, let me make this a bit bigger. You all know what free and bound variables are already, so just reminding you, because we're going to be doing an awful lot of playing with free and bound variables here. So, of course, that is bound. And here, which one is free? Which one is free? The x is free, because you see, that's y is bound, z is bound, x isn't bound. BFD. And of course, from time to time, we might have to rename a bound variable. And, okay, people differ on this, but from my point of view, this formula and that formula are the same formula. But there will be people, there is a completely rational point of view that will say that these two are logically equivalent but different formulas. So mostly it's not going to matter for us. And because we're dealing with syntax in order to express our formal proofs, we need to be able to substitute for bound variables. This is, again, totally routine stuff. In fact, this kind of thing is very easy to code in ML or something like that if you want to write code that will represent terms and formulas and substitute. And by the way, if you go to the course website, there is a little computer program in standard ML, that's the theorem prover. I had that code sitting there for about 20 years, and a year or two ago, a student tried to run it and discovered that it didn't run because it made some assumption that was valid in something like 2002. So I updated it, and if any of you want to play with a little theorem prover that I wrote, it is there. Of course, there are tons, if you really want to fool around with this stuff, there's tons of theorem proving stuff you can download and run on any kind of machine you've got. But if you want to roll your own, it's very easy in a functional programming language. And the reason I said all that is trying to motivate that all of this stuff here is just the obvious recursion that you would write in a functional programming language. So when I write this weird notation here, we can pronounce this A putting T for X, meaning that it's a formula A, except I'm replacing the variable x by the term t in a systematic way. And I guess we could also talk about substitution within a term. So if I have some term u, you could imagine replacing every occurrence of x by t. It's not a complicated idea. So for example, again, the obvious recursion, if I'm substituting for a variable in a conjunction, the result is simply the conjunction of the substitutions in the two parts. Nothing fancy going on. Here it's a little trickier. So the only complicated case is when you've got a variable binding going on. And there are two possibilities. One is that you're substituting for the exact variable that's being bound. Please don't say for all t at this point, because it's a binding occurrence. What you do here is say, okay, x is not free in for all xb, therefore the substitution does nothing at all. And of course, you're all Chomskys, you've all coded, you all know about scopes and local variables and so on, so this shouldn't be any problem for you. If the variables are different, then you substitute inside the body as normal. The only danger to be aware of here is that now y is a bound variable. If the thing you're replacing x with has got references to y in it, the result is not going to make sense anymore. That's called capture of a bound variable. So if that happens, we're going to, things will be all scrambled. What do we do about that? Well, either we say it is forbidden, or equally you can say we're going to automatically rename y to something else so that that kind of thing never happens. And that's why I have this sentence here. So here I have it as forbidding it. So when you are replacing variable x by term t, none of the variables that are in t are allowed to be occurring somehow bound within a anywhere, because you could cause this absurd thing to happen. And I have an example here at the bottom just to kind of hammer this home, although I hope it's kind of obvious already that it doesn't make sense, but let me do this anyway. So the formula there that I've kind of boxed in with pieces of paper, because my PowerPoint skills aren't so great, is, it says there, for all y, x equals y. Right, that's a meaningful thing to write. Now, it may seem a little weird to you. So it's basically saying that x is equal to everything. And that can only be true if you got, I mean, you can have a universe with just one thing in it. It's a very lonely universe, but if you've ever read The Little Prince, you've all read The Little Prince, right? You got this planet with one guy on it. Okay, so you could imagine a universe with just one thing in it. And in that universe, you know, this formula could even be true, because everything is equal to x. Now, if I replace x by y, I am capturing, so this y, which is now going to be grabbed by that quantifier, and change it to for all y, y equals y, which clearly is a very different formula and is true. You know, it's a valid formula, it's true in every model. So clearly this kind of substitution is not a sensible thing to do, and so I hope none of you are intending to do it. Now, we're going to need substitution later when we write our inference rules and so on. But then, and again, I'm repeating myself, but I hope the repetitions help things make sense to you. As we did with propositional logic, we're going to focus on certain transformations that we're going to need in order to build our various proof procedures. You've probably seen them all already, so I'm drawing your attention to particular ones that will be important. For example, not for all is logically equivalent to exists not. I hope no one has an issue with this. By the way, if you are an intuitionist, you know, I mentioned constructive logic intuitionism a little bit in earlier lectures as a non-examinable aside, and maybe I even mentioned that they don't believe this, right? Because they would say just because the left side is true, just because I don't know that not for all x, that doesn't exhibit for me this x. So intuitionists don't like this, but then intuitionists can't use our proof procedures either, and their life is altogether a lot more difficult. Which is why we don't do it here, but you might find yourself doing this stuff in part 2. What else have we got? This thing, which is kind of obvious, that the formula for all xa is logically equivalent to for all xa ANDed with any particular copy of the body A with different terms plugged in for x, because that's what for all means, right? So you could, if you want, imagine, in fact, I think it's even true, that anything that you can prove, you could also, obviously proofs are always finite, so you only need to finitely number instances of every quantified formula. And in fact, if you could be told in advance how many instances you needed, first-order logic would actually become decidable. Finally, we have a distributive law here. And I hope this one is obvious, but this is a bit like saying, okay, everybody is alert and everybody is, I don't know, bouncy, is logically equivalent to saying everybody is alert and bouncy. And I think you can just imagine in your mind, okay, yeah, we're all alert and bouncy, and it doesn't matter how you quantify it. And that needs to be contrasted with this. This is not a theorem. So that's like everybody is happy or sad does not imply either everyone is happy or everyone is sad, right? That doesn't work. And by the way, as I say, you often know exam questions where they are asked to give a counterexample. Giving that example about happy or sad is not really enough to give the full marks, right? You need to be a little more mathematical. It'll probably get you half the marks, but I would prefer you to be a little more mathematical if you give a counterexample. And the usual thing at the bottom, as with propositional logic, we enjoy full duality in first-order logic. Duality means, remember, that in a formula that doesn't have funny things like implies and if and only if that have hidden nots in them. So in other words, in a formula that merely has for all exists, not, and or, you can exchange those two types of quantifiers, exchange those two logical connectives, and you will get another theorem where you had a first theorem. So this thing also holds if we exchange the role of exists and for all. That can be exists or, and this can be exists or exists, etc. So we'll need those equivalents, as I mentioned. The other thing that we sometimes talk about doing with first-order logic is increasing or decreasing the scope of quantifiers. Now, some of this looks a bit weird. The point here is that we are talking here about a bound variable x and a formula b that doesn't mention x. So if we think about the formula A, presumably does mention x, and so whether A is true or not depends on the value of x. But whether B is true or not doesn't depend on x. So if you like, we can think of B as being simply true or false in connection with any particular interpretation. We fix all the variables except x, and now in that situation, B is true or false, in which case it's kind of obvious that, say, this is true because B doesn't depend on x. So whether you move it in within the scope of the quantifier like that or not, the truth value of B won't be affected. B will either be false. If B is false, both sides are false. Big deal. If B is true, the and B's will cancel out. Well, the and B's will be a no-op, so to speak, and we will, on both sides, have for all xa. We have the same thing for or, exactly the same reasoning. This one looks weird. Why does this one look weird? It's because implies has a hidden not in it. But if this bugs you, just expand this implies so that the hidden not comes out, and then you will see that. And this will trip up everybody, so be alert to that. Now, what do we use these for? You see, when we turn to this proof procedure called resolution, which we'll get to in a lecture or two, we are going to be getting rid of all the quantifiers in formulas. And I think when people talked about this in the beginning, they wanted to be nice and tidy with the quantifiers, because of course you could have a fairly arbitrary nesting of quantifiers all over the place. And They wanted to make things look kind of beautiful because it makes things easier to explain. So they'd say, let's pull all the quantifiers to the very front of the formula, which you can do by applying these rules. You see, if you've got a thing buried deep inside, you just keep expanding the scope of the quantifier by applying these rules over and over again until all the quantifiers have the maximum scope and they appear in a nice little string in the front of your formula. That looks beautiful, and it makes certain things very easy to explain. It was actually noticed, rather sadly, and many years later, that if you do this, you are making potentially the proof of the formula becomes so much longer. I think I said this in another occasion, a so-called non-elementary increase. Non-elementary basically means that there is no easy way to write down how much worse the proof gets in terms of length. It's like a stack of exponentials is not enough to describe the increase in length. So pulling quantifiers to the front is actually a really dumb thing to do, and what generally turns out to help almost any proof procedure is to minimize the scope of quantifiers as much as you can. So if you find that you're ending it with a thing that doesn't depend on the bound variable, just squeeze the scope in, and that will turn out to help almost anywhere. Right. Okay, oh dear. This is another vestige of virtual lecturing. I would normally have tried to write this out in a fairly naff way on a second projector, but I always used to get into trouble anyway. The reason I want to talk for a moment about lecturing by equivalence is because it's mostly a dumb idea. So we're doing things like the sequent calculus. We're having these branching proofs. Later we will see resolution proofs. But there was a big push, especially in the USA, and especially urged by people like Edgar Dijkstra. Does the name Dijkstra even mean anything to you now? Some still do, yes. He had quite a cult following. He's a smart guy, but not everything he said was right. So he believed in proving everything by equivalences, and if you think that having to learn something like 12 sequent calculus rules is a pain, wait till you have something like 150 transformations on formulas to use his wonderful equivalence method. Nevertheless, there are certain occasions when if you're reasoning with logic by hand, there are a few occasions when transforming things by equivalences is actually more efficient than doing a whole kind of sequent thing. So just a very simple thing. So what am I writing here? In P and Q. So let's say you are looking at something of the form, sorry, that's an or. You are looking at something at the form P or Q. We can simplify Q assuming P equals F. What do I mean by that? Well, it's just as simple as this. If P is true, the whole thing is true, and the Q doesn't matter at all. So we may as well assume that P is false and ask what happens then. Of course, when P is false, we're going to get the value of Q as the result, as the value of the whole expression P or Q. So that is why it is logically correct that if you are looking at Q and you see something that depends on P, you could assume P is false there. Maybe a little more obvious, if you are looking at P implies Q, it's perhaps obvious that if P is false, here the whole thing evaluates to true. Here, if P is false, the whole thing evaluates to false. So again, you can assume that P is true when you're looking at the formula Q. Now, why am I saying all this? I need to give an example because that sounded like complete gobbledygook. So here's a little example, and it really is completely trivial. You see this formula, which is kind of dumb, right? It just says there exists an x, x equals a and p of x. Yeah, I choose simple examples because complicated ones would confuse you even more. So you can all see immediately, I hope, that this is the same as p of a, right? Because if there exists an x equal to a and satisfying p, then that is the same as p of a. But how do we do this formally? Well, as I said on the previous slide, when you're looking at a conjunction, we're looking at the formula x equals a and p of x. We may as well assume that this left part is true. That is, we may as well assume that x is a, which means I can plug an a in there. So I plug an a in there. Now what can we do? Well, this p of a doesn't depend on x anymore. So by the other rules I showed you for contracting the scope of a quantifier, we can bring the quantifier in like that. Now p of a has come out, and this formula on the beginning part simply says there exists an x such that x equals a, which is simply true because a is the answer there. So this is a completely formal and fully equational proof that that formula there is the same as this formula there, or rather is logically equivalent to. Okay, and I know that looks really stupid, so let's look at this one instead. This one looks crazy, right? Does anyone believe this is true? Well, it's a theorem. If I may make another one of these asides about intuitionistic logic, it is not true if you're an intuitionist, but it's true for us. How can we prove this? Well, all we have to do is notice that the right side of the implies symbol there doesn't depend on z. So we're allowed to contract the scope of the quantifier, and when we do that, it turns into a for all. And now that looks true, doesn't it? This is saying if for all x p of z, then pa and pb. Well, that's obvious, and yet this looks incomprehensible. And if we want to grind through it tediously, we can mention that, yes, of course, this for all z p of z is equivalent to ANDing it with particular instances, just to make it completely obvious. So this formula here turns out to be rather tricky to prove with any simple-minded proof procedure. So if you were to try coding your own, and if you were doing it naively, it would probably fail for that. Okay. I wanted to have one last distraction before we get to the sequent calculus. So a couple of lectures ago, I brought in that white paperback book, right? That was Principia Mathematica. Now, the first order logic that we use today is kind of descended from this book. In fact, there were early papers that referred to the formalism of Principia and things of that sort. Now, Principia was a kind of an awful mess in many ways, and the logic it gave you was really what we would now recognize as higher order logic. As I said, I was very disappointed to discover recently that they are now charging an arm and a leg for it, even though it's just a paperback, and it used to be like £7, and now it's something like 80, which is a disgrace. But if you're interested in paradoxes and in the history of logic, there is some parts of it that are actually written in English that talk about quite a few paradoxes, like a couple of the ones I gave you in the first lecture. Now, it's an amusing story that this book, what did they have to pay? Well, these sums of money look kind of comical. The Cambridge University Press didn't want to publish the book because they thought it would lose a lot of money because it did not have the look of a bestseller on it. So the authors had to pay to publish the book, and they got a further amount of money from the Royal Society. And as I mentioned here, these sums you have to multiply by 100 if you want to think of what they were talking about. So imagine each guy paid the equivalent of £10,000 to publish this wretched thing, which, remember, looks like that inside. And they had to write it too. They had to sit for years and years working out these extremely tedious proofs of these formulas. And by the way, can you see the bottom there, the bottom line? Right? And can you see the page number on which they proved 1 and 1 is 2? Okay. This is not how it's done anymore. Right. So we're going to prove, I don't know why I gave you such a long song and dance before giving you the sequent calculus, but I know why. It's because the sequent calculus is not the only proof system we are going to see here. It is merely the first proof system. You remember, I hope you haven't forgotten the sequent calculus from before, so everything else is the same. We are going to have our same rules for and or not implies that we already have, so they will be added. These new rules will be added to what we saw before. How can I explain these rules? Well, this for all on the left is one of the easiest to understand. So, and remember, we always imagine this backward because we always imagine we are given the ultimate goal of proving this thing on the bottom, let's say something of the form for all x a, whatever, and then we ask ourselves, what should I do? How can I go about proving this thing? And this rule says one way you can arrive at a thing that has for all x a in the left is if you proved it from some particular instance of a like that. Because clearly if your thing follows from a particular instance of a, then it will certainly follow from for all x a. Now, if we operate backwards, in other words, to say, I'm trying to show this, therefore I will show that, this has the unfortunate effect of throwing away this quantified formula. Now this, of course, the quantified formula is a powerful assertion because it says a holds for every possible value of x. So you might want to keep hold of this formula so that you might want to use it again. And so I'm suggesting here that you only need to stick in this one t and then you're done with it. But remember, these left-hand sides are set, so you can imagine, if you like, that you've got extra copies of for all x a that are sitting there in gamma so that you can use it more than once if necessary. Now, normally, I don't like to set problems too often that need more than one instance of a quantifier because they tend to be kind of hard, and it's not a very nice thing to do to a bunch of nice boys and girls. Occasionally it happens. So you need to be prepared. In general, you may have to keep this for all on the left side in case you need it a second time. What about having it on the right? So if you have ever done a normal mathematical proof where they typically have the form every x is a y or whatever, so you begin by saying, let's just choose a fixed thing, assume that it has the property x, then show it has a property y. So you assume an arbitrary thing for which you prove your theorem. So what is going on with this rule here for all on the right? We're proving some formula A, which involves some variable x about which we know nothing. So if I can prove a property of x and I know nothing about x, then surely that thing will hold for all x. That's what this says. Now, we have to be careful, and so there is a syntactic constraint on this rule, because I just said we prove it for a, mentioning a variable x about which we know nothing. But what if you had some assumptions about x, say, in your gamma? Then suddenly x would not be arbitrary anymore. And so I have a little example here of something that's stupid. So if you forgot this to enforce this requirement that the variable mentioned on the right is not mentioned anywhere else, then you would prove something stupid like this. So this looks kind of like a syntactically valid proof, except it's not respecting this rule, this requirement here. And you see, because it says, well, if p of y on the left, then certainly we have p of y on the right. So that's certainly a basic sequent. Now, if you are allowed then to apply for all on the right, then you have proved a sequent that says, given p of y on the left, we have for all y p of y on the right. And then if you're able to prove, let's say, p of 0 or something, then suddenly you have proved for all y p of y, and that, of course, makes no logical sense at all. So, and luckily for you, many of the things that you'll try to prove will be intuitively true or intuitively false, and that will help prevent you from making stupid mistakes like that. On the other hand, many of the other things you will try to prove will not be intuitively true or intuitively false, and then, well, it's better to give up on a proof, by the way, than to do a thing that's actually wrong. Okay, so here's a very, very simple example. And if you were given, let's say, on an exam or something, the requirement to prove that thing in the sequent calculus, I mean, it would be given like this. Very typically, prove the following sequent or find a counterexample. So remember, you write it at the bottom, leave some blank space above, because you want to complete the proof working upwards to see how you could arrive at a thing that has this as its conclusion. And you can look it over first and ask yourself if it makes sense. And what does it say? On the left, we're assuming, remember on the left the things are things we're assuming to be true. We're assuming p is true for all x. That's a nice strong property. What are we asked to show on the right? We're asked to show that p is true for everything of the form f of y. Well, that looks intuitively true, so we can't go wrong. Well, of course, you can go wrong, but you shouldn't go wrong. Now, there's a very important thing here in the case of quantifiers. See, for propositional logic, when you had a choice, like here, remember, we can work on outermost symbols, and we have two outermost symbols. They're both for all. I said, and it's true, for propositional logic, it doesn't much matter which choice you make. Here it really does, because to do for all on the left, I need to plug in a term. And what term could I plug in? I don't really know. In particular, you might want to say, let's plug in f of y here. Anyone know why we can't do that? Well, if we plugged f of y in here, then we would want to continue the proof and then introduce this for all later. And we would violate that rule I just showed you, that condition, because y would be free in the conclusion. And strictly speaking, the point is, at this point, we don't know about any y. That's an effing bound variable, right? So it could, if you like, it could change to z at any moment or something like that. So this y is not available for us to talk about. That means we have no idea what to put in for x, and therefore you should leave it alone. In general, you should postpone a for all on the left until you've done any for all on the right that you're able to do. We will do the for all on the right instead, which merely involves throwing the quantifier away. And remember, we have to check that syntactic condition says, why not free in the conclusion? And it's certainly not free. It's bound here, and it's not free anywhere. So we can apply for all on the right. And now the quantifier has gone away, and now y is a free variable. Now we know what we can put in for x, namely f of y. We do that, and now it's a basic sequence, so we draw that little line above to say, I'm finished, hooray, etc., etc. Let's make something a bit messier. Oh dear. You might notice here, incidentally, this is one of those moving a thing out of the scope of a quantifier is what this is. So this sequence is saying that this formula with p inside the quantifier implies that other one with p outside the quantifier. So what do we do? Well, we have two possibilities. We can do the for all on the left or implies on the right. As I told you before, to do for all on the left, you need to know what to put in here, and we don't yet. So we're going to leave that alone. We're going to do the implies on the right instead, which will have the effect of bringing that p over to the left side. Now what do we do? For all on the left, for all on the right. As I told you last time, it would be wise to do for all on the right first, so we do that. And now, and by the way, it is okay to do that because y is not free in the conclusion here. Now p, by the way, is just a propositional letter. So no variables are free in p. So y is not free in the conclusion there, which means I can do for all on the right. Now what do we do? The only thing left is that quantifier there on the left side, so we do a for all on the left. What term do we use? Well, we're going to use y, of course. Incidentally, this what term do we use? Here we're going to use our insight. Later it will turn out that the choice of what to plug in for a quantifier becomes very tricky if you're automating this. And we will discuss one way later in the course, one way of inventing or choosing the term to plug in here. But it turns out in general, in fact, it is still a topic for research. But here we just put in y, and then the rest is propositional, so implies on the left, blah, 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 out it comes. So that's straightforward. Now, let me give you the exists rules. Now, before you complain about how much you have to memorize, let me promise again, by lecture 12, they will be down to only three rules for the entire sequent calculus. And already here, you might notice some duality or some overlaps with the for all. So the exists on the right rule has a lot in common with the for all on the left. This is maybe more intuitive to you. So if I'm trying to show that, I don't know, a certain thing exists, you can say, yeah, it's a silly bobble hat exists, right? Yeah, I can point to it. That's the one right there. So it's the idea that to show an existential claim, you exhibit a particular t, making a particular term that you can plug in to make it true. Oddly enough, so that whole thing I said about for all on the left, namely that you might need the quantifier more than once, also applies here. So the most evil exam question you could ever face would involve a formula where to prove it, you would need to use exists on the right twice with the same quantifier. So you can, in general, keep hold of this on the right-hand side when you work upwards doing a derivation, because in a couple of weird cases it will be needed to be used more than once. And I can guarantee if you are using it more than once, then the thing you are proving is not intuitionistically valid, in fact. Okay. Exists on the left, so this is dual to the for all on the right, and it's kind of saying if I have a theorem that says there is a spotty elephant, then according to this, this basically says the spotty elephant is X, right? Okay. So exists on the left is now the thing that has that syntactic condition that the variable here mustn't be mentioned anywhere else. So if I have a theorem that says X is a spotty, that there exists a spotty element, I can call it X, but not if I already have an assumption that X is 0 or something like that. 0 would not like to be confused with any kind of elephant. And so the variable being exposed here when you strip off the quantifier has to be absolutely fresh. The same as with the for all on the right. What is the last bit of the slide saying? We saw this formula already, right? If you want to prove it in the sequent calculus, you will need to use exists on the right twice. Now, you might want to try it for fun. I'm not doing that here. Maybe I should, but I become awfully lazy in my old age. So let's instead, here is a distributive law. So, yes. We first of all ask yourself, is this true? So, exists X, PX, this could mean like there's a Pembroke student here, and exists X, QX could mean there's a Queen student here, and on the right side it says, there's someone here who's either a Pembroke or a Queen student. So that seems plausibly true. Does not work with and, right? So, right, if there exists someone here who's male and there exists someone here who's female, it does not imply there exists someone here who's both male and female. So it does not work with and. It works with or. We will see the other example on the next slide. So what do we do here? Well, outermost symbols are or on the left and exists on the right. So just as for all on the left cannot be used unless I know what term to plug in, the same holds for exists on the right. So you might be tempted, you might not even be that tempted because there really is no idea what to replace y with at this point. So we leave that there and say, okay, we're going to get rid of the or on the left instead. That's easy. We've already done that, and we know what to do. We have two copies of this thing. Either exists XPX, that's one possibility. The other one is exists XQX. And these really are symmetric, so I am wholly justified in omitting the second half of the thing. What now have we got? Exists on the left, exists on the right. Now remember, exists on the left will make a variable free for us, and that will allow us to do the exists on the right later. So X is not free in the conclusion. Therefore, exists on the left is allowed. And now we have no choice because the only symbol left is this exists on the right, and we know what to plug in, namely X. And then the rest there will be trivial, and on the other side the same thing will happen. So that's how the existential quantifiers work. You might find this as boring as, I won't use a bad word, it's boring as France, let's say. But at least if you're interested in logic, it's fascinating how these things actually work and give you the right answer. So here is the other example. So I already told you that the distributive law with exists and fails. So what are we going to do here? Well, as I said before, exists on the right you shouldn't do until you have some particular term to plug in. So we get rid of the and instead. Now we have the two things. Well, if you like, we have the Pembroke student, the Queen student. The Pembroke student is called X. Which of you is X? Well, okay. There's an X. Now, we were able to do exists on the left because the X was not free in the conclusion at this point. But now X is free here. So if you want to imply exists on the left for this one, you need to rename the variable. So we call it, what did we call it? Y. It's a good name. I was thinking it was X prime, but whatever. Y is also good, a bit more legible. So the Queen student is called Y. Now when we're looking for the student who's a member of both Pembroke and Queen's, which would be highly irregular, and we discover that you can put in X, you can put in Y, indeed you can put in Z if you wish, but none of those are going to give us a basic sequence. Now, strictly speaking, I haven't shown you that the proof is impossible. And this is where, so the question, and you see lots of exam questions have said prove or find a counterexample. So at this point, you would have to make a thing, a model. The model would need at least two individuals. So one would be the Pembroke student, the other would be the Queen student. You'd have the two predicates, and P would be true for the one individual, Q for the other, and have the intersection of P and Q being empty. And then you have mathematically created a counterexample to this formula, and that's how you would exhibit a counterexample. So, but in fact, I will quit after saying this one last thing. This turns out to be a complete calculus, which means any formula you write down, if it is a valid formula semantically, remember all interpretations evaluate to true, then it will have a proof. And therefore, if there is definitely no proof of the formula, then it is not a valid formula. Okay, that's it for today. Thank you.